Hello students, welcome to this lecture number 1 on the chemical equilibrium. From this lecture onwards, we will going to discuss the different aspect of the chemical equilibrium in your class 11 chapter, and different things we will learn, and that is will be the based on the NCERT book. So in this lecture, we are going to discuss the very first thing, very basic thing, that is the basics of the equilibrium, the type of the equilibrium. Then we will discuss different examples of equilibrium, and last we will discuss the general characteristics of the reactions when it is in the equilibrium. So this is K.K. Mukherjee in the Science with Mukherjee Sir YouTube channel. So today's lecture is chemical equilibrium. Chemical equilibrium is very important in many biological and environmental process. One example can clear it very well. That is the equilibrium between the oxygen and the protein hemoglobin plays a very important role in transporting the oxygen to the body cells from the lungs, and the transport of oxygen is very much essential for the living organisms. Without this oxygen you cannot able to live. So equilibrium is so much important that we can understand from these examples. So now question arises, what is equilibrium? What is equilibrium? What do we mean by the equilibrium? Equilibrium is basically achieved by those reactions which are reversible reactions. What is reversible reaction? The reversible reaction is those reactions where the reaction or the physical process, when we are talking about the equilibrium, we will be considering these two things, two processes, that is on the physical process and another is your chemical reactions. And the equilibrium is possible for this reversible reactions. Now what is reversible reaction? Let us understand. Suppose this is a reaction. A and B is reacting and it is going to give the C and D product, right? For this reversible reaction, this notation you will be always to be given. This is the double half arrow. You can see this is a half arrow and this is a half arrow and this is double half arrow. This signifies that the reaction is going on both the directions. That is A plus B, when it will be give the C and D, it will be the forward reaction, and you can write this. This is forward reaction. This is forward reaction, right? This is forward reaction, and C plus D, that is your backward reaction. So in the reversible reaction, you can always see that there will be the forward reaction and the backward reaction. Now what is equilibrium? Equilibrium is this type of reaction will achieve the equilibrium stage. It is basically stage of the reaction. Equilibrium, we can write it, it is the stage of the reaction. Equilibrium So this is the condition of the equilibrium. We will say this reaction has achieved that stage, or reaction has reached that stage when the rate of the forward reaction, that means this, when AB will produce the CD, that rate will be equal to the rate of backward reaction. That is, when CD, this product will react with each other and it will produce this A and B. So when the rate of this forward reaction and rate of the backward reaction will be equal, we will call it is the reaction has reached to the equilibrium point. Okay. Now we will understand the type of equilibrium. Second point that we need to understand types of equilibrium. So there are two types of equilibrium, that is one that is the physical equilibrium, another that is the chemical equilibrium. First let us understand what we mean by the chemical equilibrium. Physical equilibrium first let us understand. Physical equilibrium is those applicable for those physical processes in which there is a change of physical state of the matter is observed. As for example, for the physical equilibrium, you can see we have given some example here. That is first that we are discussing now the physical equilibrium. First, that is solid to liquid. Different phase transformation are the most simple example of this physical equilibrium. Physical equilibrium, that is solid to liquid. Solid to liquid, one of the very simplest example of this phase transformation, where you will find the solid has been transformed into the liquid, and its example you can see. First let us write down what are those physical equilibrium physical process that we are going to discuss later on. So that is solid to liquid, then liquid to this notation will be given like this and this. Then liquid to gas. Then we will discuss the solid to liquid directly, solid to liquid. Then fourth we will discuss, that is solid to solute in solution, and fifth we will discuss gas in the gas state to the gas in solution, that all are we will going to discuss, and this will give you the lot clarity about the equilibrium. What do we mean by the equilibrium when we study this physical process, that is the phase transformations? Okay, one by one let us going to understand. Of the solid and liquid is ice water equilibrium. Ice water, that is solid H2O. What is solid H2O? It is ice. And what is water? That we know, we always used to drink in day-to-day activities. This is the most commonest example, solid to liquid phase transformations. Normally, when we put a solid, that is a ice, in an open atmosphere, what will going to happen? After some time it will melt. But if we keep this solid, that is ice and the water, in a thermoflux, what is going to happen? Now there will be no heat flow from the outside to the constituents, that is the solid, ice and the liquid. So after some time at a temperature 273 Kelvin and at atmospheric pressure, what you will find? You will find that physical process has reached at equilibrium. We can say that it reached at equilibrium stage. Equilibrium stage. And in that stage, what you will find, that is a very interesting thing, that the mass of the ice and water become fixed, become constant. So we can write one thing, that is observation. The mass of become fixed, means constant. It looks like that after that there is nothing is going on, means everything has stopped, because the amount of the ice and water that is completely remain unchanged with the time. But this is not the case. Case is that there is a intense activity at the surface boundary between the ice and water. What is this activity? Activity is that rate of, you can write rate of melting become constant, become fixed. The rate of, that is because of this fact only, the rate of melting of the ice and rate of freezing of the ice become constant. So there is no net melting or no freezing. That is why this water, this constant, it became constant. The reason is this. Okay. So at that point, and obviously this has achieved at a particular temperature and particular pressure. So the operating pressure became constant with this mass and ice of the water becomes constant, because of the fact the rate of melting is equal to melting of ice is equal to rate of freezing of the ice. That is means this physical process has reached to the equilibrium stage. And we will say one definition is comes out, that is the melting point or the freezing point of the substance, of the pure substance, that we can say, that is that at a particular temperature, at a given temperature, the temperature at the atmospheric pressure is called the melting or freezing point, when the ice and water coexist in equilibrium. At the equilibrium, at the temperature in which the equilibrium has been established between the ice and water, we will call it is a melting point or normal melting point or normal freezing point. So we understand this physical transformation, solid and liquid, that is ice water equilibrium. At the equilibrium point, you will find that is a constancy of the amount of the ice and water, and this is because of this fact that the rate of melting and rate of freezing of the ice is same. Similarly, we can have another phase transformation, that is, we know that is liquid and its example, very simple example we want to quote, that is liquid H2O is being kept in a container which is closed, and we will find this is example. When we keep a liquid in a closed container, what is going to happen at the room temperature? The surface of the molecules of the liquid will be highly energetic and it will evaporate. It will go in the vapor stage. But this evaporized water molecules again will return back to the water surface, and this process is continuing, and time will come when there we will be able to achieve a constant vapor pressure, and this is also called the equilibrium vapor pressure. That can be experimented in your laboratory, that you can see that You take a container, and in this container you put some water glasses which is having some water, and after some time, which is free of any moisture, after some time, if you have the arrangement of measuring the pressure inside it, you will find after some time this pressure become constant. And this constancy is achieved due to this fact that at that time this process, that is this physical process which we are talking about, the liquid to gas, has reached the at equilibrium. So we can say like this way, that is in this case of a phase transformation, at equilibrium, what is going to happen? This equilibrium. At equilibrium, what is going to happen? The rate of vaporization, we can say not vaporization, it's evaporation. Rate of evaporation is equal to the rate of condensation. That we can already discuss that there is a process, two reverse process, that is rate of evaporation and is equal to the rate of condensation at the equilibrium point, and you will find a constant vapor pressure because there is no net evaporation. So there is no net evaporation due to this fact. These two, rate of evaporation and rate of condensation, become equal, and that is why this has happened. So this is the second. And third, that is we are going to discuss, that is the solid to gas. There are some solid like your solid iodine or solid camphor or solid ammonium chloride. You will find there is a tendency to bypass one state, that is the liquid state. It will directly go to the gaseous phase. It is called also the sublimation. And this is the example we are taking, that is the solid iodine. Iodine solid is equal to iodine in the vapor form. And when it reached a equilibrium, what you will find? You will find a very interesting thing, that at that point the rate of sublimation of, you can write here, rate of sublimation is equal to rate of condensation. So what is going to happen here in this transformation, phase transformation, that is the iodine solid has been evaporated into sublimate. We'll call this process sublimation. Into this, initially the sublimation will be higher, and this will be indicated by the color of the container. Color of the container will be deep blue color, and this color will be goes on increasing, and after some you will find the color become constant, means after it reached the equilibrium stage. So we understand all this from this physical process, that at the equilibrium what is going to happen? It is going to happen that a quantity is fixed. That is, in this case, the solid liquid, you will find the water and ice become fixed. In the liquid gas, you will find the vapor pressure is fixed, constant. In solid and gas, you will find the color of the iodine become a constant one. So at equilibrium, what is the most important thing? That the quantity of the substance that we are taking, that we are making the experiment, that is become fixed. And why it is become fixed? Because there is a dynamic nature of this equilibrium. At that time, the process is still going on. The process is not stopped, but as if it looks like that process has stopped, but it has not stopped. So we will go through these three very important phase transformation or physical transformation, and from this we can able to understand what is really a equilibrium is. Okay. This is one of the physical transformation that we are going to discuss, that is solute solid. S means solid and solute solution. The example is sugar solid and sugar in solution. Sugar in solution. We know that when we are going to prepare a sugar solution, at room temperature, when we give some sugar solution, sugar in that water, in the solvent, what is going to happen after some time, that no further sugar will be added to it. But we want to make a thick syrup. What we will do? We have to give temperature to this, and that is why at that time the high temperature the sugar will be much more sugar will be dissolved. What is going to happen? Because of the saturation point has achieved, the further sugar will not be taken off by the sugar solution. And what is going on at this saturated point? When the sugar solution is saturated, there is also a equilibrium point is reached. There is also a equilibrium point. So we can write one thing very important, that at equilibrium point, rate of dissolution. What is going to happen? The sugar is being dissolved. Sugar has been dissolved in the water. So we can write rate of dissolution of sugar is equal to rate of crystallization. Rate of crystallization. So these two things are going to be very important in that equilibrium. At the equilibrium point, the rate of dissolution of sugar and the rate of crystallizations at a particular temperature. We always remember in mind the equilibrium point has been reached for a particular operating conditions, that is temperature and pressure. Here you can see rate of dissolution equal to rate of crystallizations. At that point, what is going to happen? What is going to happen? At this point, you will find that the sugar solution which is being dissolved, the number of sugar molecule has been dissolved and the number of sugar molecule has been crystallized will be equal. The rate is equal. That is why you can find that when we are going to add on the sugar, after some time it do not want to take much more sugar, because at that time what is going to happen, these two things, that the rate of dissolutions and the rate of crystallization become equal. At that time which you will not find further sugar taking up by these solutions. And this equilibrium point have the dynamic nature, as if it looks like that reaction has stopped, process has stopped, but it's not like that. At that time you will find that this process of dissolution of sugar and this process of crystallization of sugar still there, and this can be proved by taking the radioactive sugar. Radioactive sugar, if we put this radioactive sugar in this saturated solution, what we will find after some time, the solution having which is not have this radioactive sugars, it will have some proportions of radioactive sugar, and the time will come, the ratio of the radioactive sugar and the normal sugar, that will be become equal. The ratio will be become equal, and that will say that this solution has reached the equilibrium point. So you understand this very important physical process. Now we are going to understand another important process, that is gas and gas in gaseous state. Gas in gaseous state and gas in the solution, in the solvent. Gas in the solvent. Gas in the solvent. Okay. Gas in the gaseous state and gas in the solvent. The example you can see, carbon dioxide gas is in equilibrium with the carbon dioxide in the solution. Carbon dioxide in the solution. This is the one of the example, and very important example that we did today. We see with the soda water. When we open the soda water, what is going to happen? The bubbles will fizz out. Why it is so? Because actually it is the dissolved carbon dioxide that is being coming out. When the bottle has, when the soda water bottle has been bottled, at that time with a high pressure, this carbon dioxide has been put in that bottle. But when we open, the pressure is released, and that is why it is because of the solubility of the carbon dioxide is different at different pressure, and that is been governed by one very basic rule that we will understand, that will in much more detail in the class 12 in the solution chapter. You will understand this. This is the Henry's law. This law states that at the particular temperature, the mass of the gas dissolved in a given amount of the solvent is directly proportional to the pressure above the solutions. Pressure above these solutions. And higher will be the pressure, higher will be the content of this gas. So what is going to happen? At the higher pressure, there is much more solubility, then much more amount of the carbon dioxide is dissolved in this solution, and when we open means we will release this, and this has been coming out, the water will come from this. So we understand this physical process also. There's a we are already understand the 5 physical process. This 5 physical process. From this process, what we understood, that we are going to discuss after the discussing of the chemical. Another equilibrium that we are going to discuss, that is the chemical equilibrium, physical equilibrium. Now we are going to discuss the chemical equilibrium. Chemical equilibrium. Chemical equilibrium basically observed, achieved for the chemical reaction, that we have already cited one examples. And this type of reaction, just like the physical processes, this is analogous with these physical processes. You can see that the reactant will react with each other and will be going to produce the product. And this, with the time, what is going to happen, if we see these reactions and if we make a graph of this, this is time and this is the concentration. This is the concentration. In this concentration, we find the with the time the reactant A or B. We have already discussed the A, B, that is CD. Reactant will be produce the product, and the reactant concentration of the reactants will goes on decreasing, and the initially when the t equal to, this is a time. When t equal to 0, this, and time will come, what is going to happen? That there will be a point will come that the composition of the reaction mixture at the equilibrium, composition of the reaction mixture will be becomes same, constant, and we will say this is point A, equilibrium point, as like your physical process, equilibrium. At that time, what is going to happen? The rate of forward reaction. Rate of forward reaction means rate of production of the C and D, rate of forward reaction is equal to the rate of backward reaction. Okay, at that time. This type of reaction, you can see the out of examples, that is N2 plus H2 gas plus H2 gas, it will going to give the ammonia. Three volume of hydrogen will react with the one volume of nitrogen and will going to produce the 2 volume of ammonia gas. This is a reversible reactions. Another example you can see, that is calcium carbonate. When calcium carbonate solid is heated, it will produce calcium oxide solid and carbon dioxide gas. This is also a reversible process. So, lot of reactions we will find the reversible process, and all those reversible processes will achieve the equilibrium at a particular temperature and process. And this equilibrium can only be achieved, that we are going to discuss the latter in the last of this lecture will be the general characteristics of the equilibrium. This is the general characteristics of chemical and physical equilibrium. Number one, the equilibrium can only be achieved when the system is closed. In closed system, we can write this very important fact: the closed system, equilibrium can only be achieved. Equilibrium can only be achieved. That is a very, very important point to understand. In the closed system, in case of ice water, you have used the thermoflux. In case of evaporation of the water, you have used a closed container. Right? Any chemical reaction, you have to use the closed container. Otherwise, the equilibrium will not be achieved. Okay? Second point, dynamic nature of the equilibrium. Dynamic nature of the equilibrium means what? At the equilibrium, the process still going on. The forward process and the backward process still going on. But their rate of forward process or you can say reaction is equal to rate of backward process or reaction, rate of backward process. Okay? Or reactions. Number third point, that is very again important point, that the amount at the equilibrium become constant. Means fixed. What we have said? Vapor pressure is constant. Thus, sugar in the solution become constant. In the gas solution, when you dissolve gas, the amount of gas become constant. Right? In this way, everything is constant. And from this amount at the equilibrium point, we will be able to understand the very important thing, that is the extent of the reaction. The extent of the reaction can be understood from the amount of the extent of reaction. Reaction can be understood from this amount. Okay? And fifth point, the equilibrium can be achieved. Equilibrium can be achieved from both the directions. From both the directions. So you can understand these general characteristics of the equilibrium that is given here. The equilibrium only be achieved in the closed system. The dynamic nature of the equilibrium, the amount produced, amount of the equilibrium will become fixed. The extent of reaction can be understood from this amount of the material in the equilibrium, and the equilibrium can be achieved from the both the directions. That is all the five very main general characteristics of the physical equilibrium. And that is all for today's video. In this video, what we have understood, most probably that will be very convenient to you to understand this chemical equilibrium chapter. That is the first lecture. In the second lecture we will discuss about the dynamism, how we can able to prove the dynamism of the equilibrium constant, and some laws are there that we are going to discuss in the next video, in the lecture 2. And till then, all the best and be best. And if you like this video, you can share to your friends. Thank you very much for listening. All the best.